Hi all. I thought today we could start off with some problems um, that people often confuse double angle formulas with. I wanted to look at these, like cosine 2x plus 1 equals 0. Yeah, I'm not using a double angle formula here. I'm doing this like we did in section 5.3, where I'm just going to subtract 1 from both sides and get cosine 2x equals negative 1. And I'm going to say, when is cosine negative 1? Well, that happens at pi, but because of this number, I'm going to go around the unit circle that many times, picking up solutions. So the first time cosine is negative 1 is at pi, and then the next time would be 3 pi. Well, that's what 2x equals. So what does x equal? Well, that means we have to divide everything by 2 to get x equals pi over 2 and 3 pi over 2. Okay? This was the 0 to 2 pi solution. If we wanted all solutions, we would start with 2x equals pi over 2 plus 2 pi n. Remember, we only pick up the first set of solutions. Pi, we only pick up the first solution, or first set of solutions if there were two. Here there's only one solution on 0 to 2 pi, or on one surround the unit circle. And then we'll divide everything by 2 and end up with x equals pi over 2 plus pi n. And we can see if we plug a 1 in here, 1 times pi is pi, plus pi over 2 is 3 pi over 2. And so our little machine that generates all solutions would certainly generate our first two by plugging in a 0 or a 1. Okay, so that's where we've been in 5.3, and then yesterday we were talking about solving. Double angle equations. So here's an example of something I would use a double angle equation with if I had sine 2x plus cosine x equals 0 on 0 to 2 pi. So I have a 2x and I have an x. They're not the same angle. I need them to be the same angle. So here I'll use my double angle formula. So when I have more than one trig function, I'm going to be using double angle formula to rewrite one of the terms. We know the sine double angle is 2 sine x cosine x plus this cosine x equals 0. I see that they have a common cosine x that I'm going to factor out, which will leave me a 2 sine x, then our plus sign, and cosine divided by cosine is 1. We set each factor equal to 0, cosine x equals 0, 2 sine x plus 1 equals 0, so we know sine x equals negative 1/2. We say, when does cosine equal 0? On 0 to 2 pi, and that happens at pi over 2 and 3 pi over 2. And when is x equal to negative 1/2? Well, we're looking for these places on the unit circle where we have a y value of negative 1/2. So we know x would be equal to 7 pi over 6 and 11 pi over 6. So we get 4 answers here. Here, I needed to use my double angle formula. How about this one? 2 sine 2x plus 1 equals 0. And again, let's look on 0 to 2 pi. There's only one trig function here. There's only one term with an angle in it. And I'm going to work and say, well, since I only have that, I'm going to not use the sine double angle formula, but instead I'm going to do sine 2x equals negative 1/2. When does sine equal to negative 1/2? Well, that happens when 2x is equal to 7 pi over 6 and 11 pi over 6, we said. But this tells me I should go around the unit circle twice, picking up solutions. So I have to add 2 pi to this one, which will be 19 pi over 6. And I have to add 2 pi to this one, which will be 23 pi over 6. If we divide both sides by 2, we end up with x equals 7 pi over 12, 11 pi over 12, 19 pi over 12, and 23 pi over 12. Now, if this were 24 pi over 12, that would be exactly 2 pi. 23 pi over 12 is just a little less, so we know that all 4 of these solutions are between 0 and 2 pi. Okay, so no double angle formula there. But what happens if we had tried to use the double angle formula? Well, let's see. So I get 2 times 2 sine x cosine x plus 1 equals 0. Okay, and that's 4 sine x cosine x equals plus 1 equals 0. Or sine x cosine x equals negative 1/4. Well, here I have a product. And it's not like I can say sine x equals negative 1/4 and cosine x equals negative 1/4. No, that doesn't work. That only works if this were equal to 0. If this is in factored form equal to 0, then I can set each factor equal to 0. So, for example, if I had sine x times 4 cosine x plus 1 equal to 0, sure, I could set sine equal to 0 and 4 cosine x plus 1 equal to 0 to get cosine x equals negative 1/4. But here, I have just thing times thing, that's my factored form, not equal to 0. I have a 0 product property, thing times thing equals 0. I don't have a negative 1/4 product property. There's an infinite number of choices of what this would be depending on what I plug in for this. So I can't solve this. So that's why I don't use the double angle formula here, even though it might be inviting. I do this as a 5.3 problem. So what do you think about this one? Cosine 2x plus sine x equals 0. Again, on 0 to 2 pi. Maybe we should do all solutions. All right, all solutions. So, 2 different trig functions. They could be the same, they could be different. More important is 2 different angles. So I need to have the same angle when I'm doing this. So that means I'm going to use my double angle formula here to get rid of cosine 2x and replace it with some x stuff. Now I've already got a sine function here. So when I use my cosine double angle, I do not want to use this one, cosine squared x minus 1, because this one will introduce cosines with sines. I don't want 2 different trig functions. I want 1 minus 2 sine squared x, because then everything can be in terms of sines. So I'm going to put this here and have 1 minus 2 sine squared x plus sine x equals 0. And I hate factoring with a negative out in front. So I'm going to factor, no, Now I'm going to move everything to the other side of the equation and have 2 sine squared x minus sine x minus 1. Here I can factor this trinomial as 2 sine x, 1, 1. Now I need a minus 1 here, and that's going to be made from a negative 2 sine x and a positive 1 sine x. This equals 0. We get 2 sine x plus 1 equals 0, and sine x minus 1 equals 0. So sine x equals negative 1/2. And we know that that happens at 7 pi over 6 plus 2 pi n and 11 pi over 6 plus 2 pi n. Over here, when is sine x equal to 1? That happens at x equals pi over 2 plus 2 pi n. So those are our all solutions for this problem. Okay, how about this last one? All of these are great test-worthy questions for the Chapter 5 test. But after this, we'll move on and cover the new material, half-angle formulas and power-reducing formulas. Okay, so cosine squared 3x minus 1 equals 0. Okay, so I add 1, I get cosine squared 3x equals 1. I take the square root of both sides. I get cosine 3x equals, remember you took the square root of both sides, so you need a plus and minus over there. And then 3x, not a double angle formula. So I'm looking to, and not a sum and difference, don't use a sum and difference here. Instead, I'm just going to go around the unit circle 3 times, picking up solutions. When is cosine equal to 1? Well, that happens at 0, at 2 pi, and at 4 pi. So we went around 3 times picking up solutions. That's what 3x is equal to. Now we have to divide each of those solutions by 3. And we get x equals 0, 2 pi over 3, and 4 pi over 3. Oh, but wait a minute. That was only when is cosine 3x equal to positive 1. I also need when is cosine 3x equal to negative 1. Well, we know that cosine is equal to negative 1 at pi, and I go around once, so pi, and then I go around once more, and I get 3 pi, and then I go around a third time, and I end up at 5 pi. But just as I divided all of these by 3, I need to divide these by 3. And so I also get pi over 3, pi, and 5 pi over 3. Those are my solutions on 0 to 2 pi for this problem. So don't forget about going around the unit circle this many times. But not always. Sometimes I want to use the double angle formula. If I have a double angle and a single angle in the same problem, I want to make them the same angle. Okay, so let's move on to today's stuff, which is half-angle formulas. Remember how a moment ago we talked about there being double angle formulas, multiple cosine double angle formulas to choose from. So, for example, cosine 2x equals 2 cosine squared x minus 1. Okay, so let's solve for cosine x. Okay, I'm going to add 1. Cosine 2x plus 1. Actually, in the book, you see the 1 over here. and we've got 2 cosine squared x. Now we'll divide everything by 2, and then we'll take the square root of both sides to undo that squaring. And as we just said, when we take the square root of both sides, don't forget that plus and minus that shows up. So over here I have cosine x equals plus and minus square root 1 plus cosine 2x over 2. Now this is called the half angle formula because this angle is half of that one. And you may say, well, why would I ever want to use that? Well, let's try this experiment. Let's say that 2x equals u. And if we divide both sides by 2, we've got x equals u over 2. So using this u substitution, let's rewrite this in terms of u's. 1 plus cosine 2x was, remember, u over 2. And out here, x is equal to u over 2. So that's why this is called the half angle formula. If I want to know the cosine of some angle and it's half of one I conveniently know, I can use the one I conveniently know to help me evaluate the value of the cosine of the angle that's half as big. Now I'm pretty sure that that sentence made absolutely no sense. So having derived one of the cosine half angle formulas, or the cosine half angle formula, I will now show you how to use it. By the way, this plus and minus here, it's not both of them. It's whichever one is needed for our angle. So for example, if I wanted to find the cosine of 22.5 degrees, well, I know that that's half of 45 degrees. So in here, I plug in 1 plus cosine 45 over 2. Now, in what quadrant is 22.5 degrees? That's first quadrant. And cosine, is it positive or negative there? Cosine is positive. So instead of having both of these, I would just have the positive version. So see, I'm looking for this angle, which happens to be half of an angle I already know. There it is, 45 degrees. So I can use the angle I know that's twice as big as this one to help me find the cosine of this one by using this formula. Okay, why don't we finish this off while we're here? Cosine of 45 degrees is root 2 over 2, and all of this is over 2. Well, up here in the numerator, I'm going to make a common denominator. And so that will bring me to 2 plus root 2 over 2 over 2 over 1. Well, I'm going to do the flip and multiply now. And so these will cancel. Oops. No, that's not what I did, is it? That's what I said I was going to do, but I didn't actually then do it. There we go, flip and multiply. So these cancel. And down here, I have 2 times 2, or 4. And up here, I have 1 times these things. So I've got square root of 2 plus root 2 over square root of 4. And square root of 4 is 2. So I've got a 2 outside of a radical, and then up here, 2 plus root 2. This is my exact value of cosine 22.5 degrees. Okay, so that was using this half angle formula. Here, cosine u over 2. Sometimes we see it written like this, sometimes we see it written like this. What's important for us to remember is that the angle that we plug in inside is twice as big as the angle we're trying to find. All right, so while we're talking about cosine half angle, let's try this one. We know that cosine u over 2 is equal to plus and minus square root 1 plus cosine 2u. Oops, sorry, cosine u over 2. So what about cosine of 75 degrees? Well, we did this with sum and difference formulas, but we can also do it with half angles, because 75 degrees is half of an angle I know. 75 degrees is half of 150. So 1 plus cosine 150 over 2. Now, some students say, well, Mr. Kukla, because cosine of 150 would be negative, because 150 is in second quadrant, this should be negative. Oh, but no, this is the angle we're talking about. This is the angle that determines the SIGN over here. Cosine of 75 is going to be positive because 75 degrees is in first quadrant. Okay? And so we're going to have square root of 1 plus, 1 minus root 3 over 2 over 2. I'm going to make that common denominator up top. And then I'm going to flip and multiply again. And so I end up with 2 minus root 3 over 4, which I can split up into 2 minus root 3 and root 4, which is 2 minus root 3 and 2. No plus or minus, because 75 degrees cosine would be positive, not negative. So I have to make that determination. It would be a shame to do all this work correctly and leave a plus and minus on the front of it so that the problem gets marked wrong at the end. Okay. So what about the sine half-angle formula? Sine half-angle. So we started off with cosine 2x equals, and we had this 1 minus 2 sine squared x formula. Okay, so let's solve for sine x. I'm going to add this to both sides and subtract this from both sides. So I'm going to have 2 sine squared x equals 1 minus cosine 2x. And now I'll divide by 2. And then I'll take the square root, and I'll get sine x equals plus and minus square root of 1 minus cosine 2x over 2. Same rules apply to this plus and minus. It depends on this angle. If this angle would have a positive sign, then I use the positive. If this angle would have a negative sign, then I use the negative. And if you like, as a reminder, you can of course write this as 1 minus cosine u over 2 equals sine of u over 2. I like this representation a little more because it reminds me that what I'm plugging in here should be twice as big as what I'm starting with. However, I would say two things about that. While I prefer that, most students look at this and say, I need to use the double angle formula. And you don't want to use the double angle formula here. And the second thing is that students seem to prefer u over 2 because it tells them, oh, this is a half angle problem. I need to use the half angle formula. Okay? So, what if we had something like sine of 165 degrees. All right. Well, we could probably do that with sum and difference formulas, but let's try with our half angle formula. I want the sine of 165 and our formula sine half angle equals plus and minus square root 1 minus cosine u over 2. Okay, so what's twice as big as this? 2 times 165 is 330 degrees. And that's my u. This is my u over 2. This is an angle that's been divided by 2. See, u was divided by 2, and this was the result. So u must be twice as big as this angle presented out here. So my formula then looks like plus and minus square root 1 minus cosine 330 over 2. Now, the sine of 165 degrees. 165 degrees is here. That's positive sine value. So I don't need the negative, I just need the positive. Oh. If this had been cosine 165 degrees though, think about that, the cosine over here is negative, and so I would use negative 1 plus cosine 330 over 2. That's how I would set up for this one. But we're doing sine of 165, and so here's my setup. We have 1 minus, the cosine of 330 degrees is root 3 over 2, over 2. I do the common denominator up top, 2 minus root 3 over 2 over 2. And yes, that is going to be flip and multiply. And yes, we are going to take one of those 2's out. And so we'll have 2 minus root 3 over 2. That's the sine of 165 degrees. Whereas the cosine of 165 degrees would be negative 1 plus root 3 under the radical over 2. Because we know that the cosine of 330 is still root 3 over 2. And I would still make a common denominator. And I would still do the flip and multiply and be able to pull that 2 out. The differences are this plus sign and this negative out in front, because the cosine of 165 would be negative. Okay, so that's our half angle for sine and cosine. What about tangent half angle? Well, tangent half angle, if someone asks you to find sine half angle and cosine half angle, then tangent half angle is certainly sine half angle over cosine half angle. So you could just divide one answer by the other. But when I look at our last problem with square root of 2 minus root 3 over 2 over square root of 2 plus root 3 over 2, I don't really want to simplify that. It looks kind of horrible. Even if I do the flip and multiply, 2 plus root 3, I get to this place where I'm looking at square root of 2 minus root 3 over square root of 2 plus root 3. And that makes me very sad. I don't particularly want to work with that one. But I can use this alternative. Tangent u over 2 equals 1 minus cosine u over sine u. Again, these angles are twice as big as that one. So if I'm looking for the tangent of, if I'm looking for the tangent of 67 degrees and 30 minutes, what I plug in the formula is something that's twice as big as that, 135 degrees. And this isn't that bad, is it? Let's see. Cosine 135 is going to be negative root 2 over 2 times this negative would give me positive 1 plus root 2 over 2. Sine of 135 is root 2 over 2. So if I tidy this up, I get 2 plus root 2 over 2 divided by root 2 over 2. If I flip and multiply, these cancel, and so now I have 2 plus root 2 over root 2. Don't you dare cancel those. Instead, rationalize. And remember to distribute on top. So I'm going to have 2 root 2 plus root 2 times root 2 is 2 over 2. And then I notice I can factor a 2 out of the top, and I'll have root 2 plus 1 over 2, and these can cancel, and I get root 2 plus 1. That's a lot tidier than we had before by using sine half angle over cosine half angle. I really like this formula. There's actually a second tangent half angle formula as well, sine of u 1 plus cosine of u. I generally like having one thing on the bottom instead of two things on the bottom, so I more often use this one, but this one can be handy from time to time as well. So there's my tangent half angle formula. And we should be able to do these problems not just in degrees, but also in radians. So if I have tangent 3 pi over 8, yeah, I don't know 3 pi over 8, but I do know that 3 pi over 8 is half of half of 3 pi over 8 is half of 6 pi over 8, or 3 pi over 4. And I do recognize 3 pi over 4 from my unit circle. So I'm going to use the tangent half angle formula for 3 pi over 8 and say tangent 3 pi over 8 equals 1 minus cosine 3 pi over 4, right? Because I have to plug in an angle that's twice as big as this one, over sine of 3 pi over 4. So this gives me 1 minus a minus, root 2 over 2, over root 2 over 2. And since we just did the degree version of this, we know that the answer here is root 2 plus 1 when we're all done. Simplify. Okay. What about a sine or cosine half angle in radians? Sine of pi over 8. I don't know pi over 8, but I know that 2 times pi over 8 is pi over 4. Aha, pi over 4 is what I plug into the formula. So if I'm looking for sine of pi over 8, and sine would be positive for a first quadrant angle like this, I'm going to use 1 minus cosine pi over 4 over 2. Well, cosine of pi over 4 is root 2 over 2. And now I make that common denominator up top. And then I flip and multiply. And that brings me to here. 2 minus root 2 over root 4, which is 2 minus root 2 over 2. And positive because pi over 8 is in first quadrant and sine is positive in first quadrant. Okay, so those are our half angle formulas. We might see some solving, but not a lot. I won't be, I don't think I'll be testing on solving, but I'll check. I definitely will be testing on using half angle formulas though. I also wanted to say another popular problem type here is the draw a triangle problem type. So they tell me to find sine of theta over 2, cosine of theta over 2, tangent of theta over 2, and they tell me that the secant of theta is 5/4 and that theta is in quadrant 1. Well, note this angle is twice as big as that one. So I'm going to be using this information to help me evaluate that half-angle formula. But first, let's draw a triangle in quadrant 1 whose secant is 5/4. Using my Pythagorean triples or my Pythagorean theorem, I find out that this is 3. Okay, so what do I need? I need to use the sine half-angle formula. Square root of 1 minus cosine theta over 2. Well, cosine of theta is 4/5. Oh, okay, so I have square root of 1 minus 4/5 over 2. Plus or minus, question mark? Well, since we're in quadrant 1, everything is positive there, so only the positive. I'll make my common denominator here, 5 minus 4/5 over 2/1. I'll simplify up here and flip and multiply, and that will give me 1 times over 5 times 1/2, or square root of 1/10, which is square root of 1 over square root of 10, or root 10 over 10. Okay, so that's sine half-angle. What about cosine half-angle? Well, remember the formulas are very, very similar. The only difference is a plus sign here, a plus sign here, a plus sign here, and so this will be 9, and this will be 3. No, this will be 9 still, and 9. And I can pull out from that 9 a 3. So I get 3 root 10 over 10. So finding the cosine half-angle wasn't so bad. I just had to change my sine half-angle a little bit. And again, we could always divide sine half-angle over cosine half-angle, which was 1 over root 10 over 3 over root 10, and I end up with 1/3 for that. But we could also use the tangent half-angle formula that we talked about before. We could say tangent u over 2 is equal to the 1 minus cosine u over sine u. Well, we said the cosine of u was 4/5, and the sine of u opposite over hypotenuse would be 3/5. So I have 1/5 over 3/5, or 1/3. Either way works fine. Okay, so we've got some draw a triangle problems. Let's do one more of those. Cosecant theta equals -5/3, and theta is in quadrant 3. So let's draw a quadrant 3 triangle and label the cosecant -5/3. Now what about this length? Well, I know this is a 3, 4, 5 triangle, but we're in third quadrant, so the x value has to be negative. Okay. So what's the sine half-angle going to be? Sine of theta over 2. Well, that's going to be sine of an angle half as big. Oh, we should talk about that because I'm not sure yet. So I'll leave that plus and minus there. 1 minus cosine of theta over 2 is the formula. Cosine of theta. Well, cosine of theta is -4/5. So I end up with plus or minus square root of 9/5 1/2, or plus or minus 3 root 10 over 10. Now, is an angle half as big as this angle, half as big as this angle, going to be in second quadrant or first quadrant? Or first quadrant, or even third quadrant? Well, let's think about that. 0 to 90 degrees. Half of anything in here would live here, 45 degrees or less, right? Because half of 90 is 45. Okay. And then if I go out to 180, half of 180 is 90 degrees. So anything where my theta is in quadrant 2 would be here. That's where the half angle lives for a second quadrant theta. Well, what about a third quadrant theta? Well, third quadrant goes between 180 and 270. Half of 180 is 90, and half of 270 is 135. So if theta is in quadrant 3, half of that would have to live here, between 90 and 135 degrees. So I know half of this theta, because this is a third quadrant theta, half of that third quadrant theta would put the answer here in second quadrant. So I know that the sign will be positive there. Let's finish this conversation though and say, what happens if I come to 360 degrees? Half of 360 is 180. And so if theta is in quadrant 4, then this is where half of theta lives. So all my half angles live from 0 to 2 pi, 0 to pi according to this picture. Positionally, half of any fourth quadrant angle is here, half of any third quadrant angle is here, half of any second quadrant angle is here, and half of any first quadrant angle is down here. Okay, so I'm going to be keeping that in mind when I'm deciding in these draw a triangle problems whether the half angle formula will have a plus or a minus on it. Okay, so we did the sine half angle and got positive 3 root 10 over 10. But what about the cosine half angle? Cosine theta over 2. Well, we know half of our third quadrant theta lives here in second quadrant, and cosine is negative there. So I have negative square root of 1 minus, 1 plus negative 4/5 over 2. Remember, the formula is 1 plus cosine theta. We know the cosine of theta from our triangle would be negative 4 over 5. So 1 plus negative 4 over 5 over 2. And we get cosine theta over 2 equals negative square root of negative 1/5 times 1 over 2, or, positive 1/5. 5/5 minus 4/5 is 1/5. And we get negative 1 over 10, which is negative 1 over 10. We rationalize, and we get negative root 10 over 10. Okay, and if I want tangent half angle, I can just take my answer from the sine half angle and divide it by my answer from the cosine half angle. So I've got, let me erase some of this. I've got 3 root 10 over 10 over negative 1 root 10 over 10. Well, if I flip and multiply with 10 over root 10, I end up with negative 3 as the tangent value. Okay, so that's draw a problems and using half angle formulas. That's mostly what we'll do. Let's just have a quick conversation about this one. secant cosecant theta equals -4 theta in quadrant 4. If I draw a fourth quadrant, -1/4 and square root of 15. Okay, so when I use my half angle formula, sine of theta over 2 equals plus and minus square root of 1 minus cosine theta over 2. All right, so where does half of any fourth quadrant angle live? Remember, we said half of any fourth quadrant angle lived here. Sine is positive here, and so this would be positive. But if I had cosine theta over 2, what can we say about whether this would be positive or negative? Well, half of any fourth quadrant angle lives over here, and cosine is negative over here. And so negative would be what I would have out in front. Okay, there we go. All right, last thing I want to talk about today are power-reducing identities. These power-reducing identities are old school, like the half angle and double angle are. But as far as usefulness, there will come something that we do in calculus that desperately needs us to use a power-reducing identity. It's a commonplace thing. We'll be doing it a bunch in second semester calculus next year. And we desperately need the power-reducing identity, or we can't do a thing. So these are really important for us, especially if we're going on in math. But what we're going to be doing with them here, after we derive one, is, what we're going to be doing is just simplifying some expressions. So let's take the cosine double angle formula again. Oops. 2 cosine squared theta minus 1. And let's solve this for cosine squared theta. Okay, so I'll have 2 cosine 2 theta plus 1. Actually, we see the plus 1 in front. Equals 2 cosine squared theta. And now divide both sides by 2. So cosine squared theta equals 1 plus cosine 2 theta over 2. Now notice two things have happened here. One, the power on the cosine went from 2 to a power of 1. So we stepped the power down. That's why it's called a power-reducing identity. But in the process of stepping the power down on the cosine function, look what happened to the angle. The angle doubled. The angle doubles every time I use angle doubles every time I use power reducing. Okay, so here's our cosine power reducing formula. Sine power reducing formula is very similar. It's 1 minus cosine 2 theta over 2. And you could take one and divide it by the other to find the tangent power reducing, but frankly, we're not going to do anything with tangent power reducing because we don't have that issue in calculus with tangent squared like we do with sine squared and cosine squared. So, instead, what I'd like to do with these two formulas then is use them to simplify some expressions. All right, let's take a look. How about sine squared theta times cosine squared theta? Well, I know with my power reducing identity that that's 1 minus cosine sorry, my brain is suddenly telling me I think I've got that formula right. 2 theta over 2. I fear my marker's running out. How about green? Times 1 plus cosine 2 theta over 2. So this one became this, and this one became this. On the bottom, I multiply 2 times 2 to make 4. On the top, I've got 1 minus cosine 2 theta times 1 plus cosine 2 theta. Here I need to FOIL. I get 1 plus cosine 2 theta minus cosine 2 theta minus cosine times cosine is cosine squared. No, you don't multiply these together. 2 theta all over 4. Well, note what happens with these middle terms. They cancel. And so now we've got 1 minus cosine squared 2 theta over 4. And you can pull that 4 out in front and have 1 minus cosine squared 2 theta. And you might say, well, surely I'm done now. And I would say, well, no, you aren't, because this is a power-reducing identity, and I've got a squared here. And we have to reduce that power, which means we need to use the power-reducing identity a second time. Remember, when we use the power-reducing identity the first time, the angle doubles. So when we use the power-reducing identity over here, the angle will double. Okay, so let's see what this will look like then. We've now got 1/4 times 1 minus cosine squared 2 theta. And I'm saying, actually, I'm going to do the distributing 1/4 minus 1/4 cosine squared 2 theta. And what I'm saying is that now when I use this cosine power-reducing identity, 1/4 minus 1/4, what is that power-reducing identity again? Well, that was 1 plus cosine, the angle doubles, 4 theta over 2. So I do a little simplifying. 1/4 times 1/2 plus 1/2 cosine 4 theta. And I distribute, and I get 1/4 minus 1/8 minus 1/8 cosine 4 theta. I can combine like terms here. 2/8 minus 1/8 is 1/8 minus 1/8 cosine 4 theta. This is what sine squared theta times cosine squared theta simplifies to. Notice lots of powers here just to the first power here. First power tells me I'm all done rewriting this. This would be a piece of cake to do our calculus on, as opposed to this, which would be a horrible, horrible nightmare. Okay, so there's 2 or 3 more power-reducing problems I'd like to do with you. How about sine to the 4th theta? Well, that's sine squared times sine squared. And we know sine squared is 1 minus cosine 2 theta over 2. And sine squared is 1 minus cosine 2 theta over 2. And so we'll have 1 minus 2 cosine 2 theta. Minus a minus is plus. Cosine times cosine is cosine squared 2 theta, all over 2 times 2, or 4. I'll split this into 3 fractions. 1/4 minus 2/4 cosine 2 theta plus 1/4 cosine squared 2 theta. And here I could certainly turn that into 1/2. But I'm not done yet, am I? Because This isn't to the first power. So I have to use my power reducing identity there. I'm going to have 1/4 minus 1/2 cosine 2 theta plus 1/4 times, and now I use my power reducing identity. And remember, whenever I use my power reducing identity, the angle doubles. So I'm going to have 1 plus cosine 4 theta over 2. I'm going to break this up into two pieces. I'm going to have 1/4 minus 1/2 cosine 2 theta plus 1/4 1/2 plus 1/2 cosine 4 theta. And then I'm going to distribute the 1/4 that's out in front to each of these things. And so I'll have 1/4 minus 1/2 cosine 2 theta plus 1/8 plus 1/8 cosine 4 theta. And 1/8 plus 1/4 will make 3/8 out in front. And so there's my answer. Please note, the first time I used the power reducing identity, the angle went to 2 theta. That's why this is 2 theta. And then the second time I used the power reducing identity, this angle doubled, and so now I have over here a 4 theta. Okay, so how would this be different if I had cosine squared 3 theta? Okay, well, so we know the power reducing identity for cosine squared is 1 plus cosine twice that angle. So this would be 6 theta over 2. Now if I had cosine to the 4th 3 theta, that's cosine squared 3 theta times cosine squared 3 theta. And so I want to use this cosine power reducing identity here and again here. So I'll have 1 plus cosine 6 theta over 2 times 1 plus cosine 6 theta over 2. This angle doubles. I need to FOIL on top, and so I'll have 1 plus 2 cosine 6 theta plus cosine times cosine is cosine squared 6 theta over 4. I'll split this up into 3 fractions. 1/4 plus 2/4 cosine 6 theta plus 1/4 cosine squared 6 theta. And then I'll say, uh-oh, another squared. I've got to use my power reducing identity again. So when I use that power reducing identity, everything else is going to stay the same. 1/4 plus 1/2 cosine 6 theta plus 1/4. But now I use my power reducing identity, and this angle has to double. I'm going to have 1 plus cosine 12 theta over 2. Inside here, I'm going to split this into 2 fractions. So I'm going to have 1/4 plus 1/2 cosine 6 theta plus 1/4 1/2 plus 1/2 cosine 12 theta. And distribute. So I'll have 1/4 plus 1/2 cosine 6 theta plus 1/8 plus 1/8 cosine 12 theta. 1/8 plus 1/4, or 2/8, will make this 3/8. And so here's my solution. Each time I use that power reducing identity, that angle doubles. It doubled once to go from cosine squared to cosine, but then when I had cosine squared of 6 theta, it had to double a second time to become cosine to the first. So that's power reducing, and we desperately need power reducing in calculus, much more so than half angle. Half angle follows nicely with our draw a triangle and unit circle problems, but mostly we need these power reducing identities next year. On your test, though, you'll see all these problems, double angle, half angle, and power reducing, showing up on the test. And that's actually the last of the new material. That's the last of the new stuff. Everything after this now we'll be reviewing for the test. So I hope this was useful. Have a great day.